Protection against bioterrorism by Group 8. Bioterrorism. What is it? It is the intentional use of harmful biological substances or germs in order to cause widespread illness and fear. This could be seen with the smallpox or anthrax. The question is, how is using germs or microbes do us any good when obviously it causes harm, as seen with these outbreaks of disease? Bacteria, the good guys, when used efficiently, can actually be used to create numerous vaccines to many of illnesses that cause serious devastation. An example of this could be seen with the polio vaccine, the H1N1 recently, the zoster vaccine for shingles, and even an anthrax vaccine made from good bacteria in dairy products. The normal flora, which we can find on our skin and in our gut, allows for the body to continue its normal function. Without the normal flora, the body isn't able to do so. So why is bacteria important? Like mentioned earlier, there are good guys, or good bacteria. These are non-pathogenic, meaning they don't necessarily cause disease. So what makes them important to human life? Well, for example, the human gut houses up to 10 to 100 trillion microbes from 500 to 1,000 species and more than 10 times the number of cells that make up the human body. And as I mentioned earlier, this normal flora in the gut allows for digestion of foodstuff and vitamins. It's when the good bacteria goes bad do we seem to be more concerned. Interestingly enough, the same microbes that cause this widespread chaos as seen with the smallpox or the anthrax breakouts, as well as their treatments, they both stem from bacteria. Anthrax, also known from the organism Bacillus anthracis, can develop spores that is deadly when inhaled, and this caused fear in the early 2000s. It's treated in its earliest stages with antibiotics like doxycycline or ciprofloxacin. So the irony is that antibiotics for this outbreak of Bacillus anthracis, known as anthrax, as well as others, are made through actually other bacteria. The overwhelming majority of antibiotics are made from living organisms like bacteria, and about 90% of antibiotics are isolated from bacteria, fungi, and even molds. So essentially, you're fighting bacteria with other bacteria. And obviously, without antibiotics and vaccines, we would have no protection against bioterrorism or outbreaks of these diseases. Examples of bacteria used for antibiotics are seen in vibromycin, which is used in doxycycline, the organism Penicillin chrysogenum, which is used in penicillin, Bacillus brevis for grapsidin, and E. coli recently for erythromycin. And these examples show how antibiotics can be harnessed from bacteria in order to treat infections. And these can be found in soil, which make them readily available. You may be asking, why would you use bacteria to make antibiotics, and how would we do this? Part of the reason is due to interspecific competition and because they cause harm to others. So how do we make antibiotics? Traditionally, manufacturers make, for example, erythromycin commercially through fermentation, using the soil bacterium Saccharopolyspora erythrea. The process is hard to scale up, creating a bottleneck in the drug development process. As erythrea grows slowly, a population of this bacterial strain takes about 4 hours to double in number. A population of E. coli, in contrast, takes only 20 minutes to double. That, plus the fact that there's a great deal already known about E. coli, is used extensively in bioscience research, makes the latter of the workhorse of choice in genetic engineering. So, harness this ability and grow and extract the genes necessary to compose antibiotic through chemistry and even recent technology. Some pros and cons of bacteria for antibiotics. One pro is that some bacteria can replicate very rapidly, as seen in the example with erythromycin and E. coli, thus giving scientists more in a small amount of time. The con is that sometimes bacteria can grow resistant to some strains, thus making it difficult to manufacture antibiotics specific to a bacteria or infection. An advantage also is using genetic technology. Some bacteria can be used to make antibiotics to strains of bacteria that are proven resistant. The machinery is highly malleable and can be even manipulated to modify natural products. Modifications may make antibiotics better to combat these resistant strains of bacteria. And another downside is, as usual, the money aspect. Some processes in genetic chemistry are very expensive, which tends to make the science industry a little weary of using this specific process. So what's the future against bioterrorism? Our main concern is recognizing the threat. A new paper describes a statistical method that can estimate an origin and time of aerosolized release of anthrax following the detection of the first few cases. The method predicts where the most critically affected areas will be following the release of this highly pathogenic agent, which may enable preventative treatment of individuals at risk and protection from this specific disease. Previously published methods can estimate basically just the date and the scale of the anthrax release, but not necessarily the source, location, or geographic extent of the human exposure. The new method uses information about the first few people infected, including when they started to experience these symptoms of infection, where they live, and where they work, combined with recent weather information, like wind direction. So basically, the take-home method is that we need to recognize that some bacteria can be used in order to harness antibiotics against things for bioterrorism, such as seen through the anthrax scare in the early 2000s. Without this good bacteria, it becomes a little bit more difficult to have vaccines and combat bacteria and infection.